Okay, calculus, we are going to review the first derivative test. Believe it or not, we've done that before. And then we're going to learn the second derivative test. So before we can do that, we need to have a little crash course review on the relationships that we've learned about functions and their derivatives. So we are going to come over here and we are going to review those relationships. So we're just going to go through it. Remember, if a function is increasing, that means it's going up from left to right, its derivative will be positive there. The graph will be above the x-axis. And vice versa, if a function is decreasing, going down from left to right, its derivative will be negative there. That means its graph will be below the x-axis. Anywhere there is a maximum or a minimum on a function, there will be an x-intercept at that x value on the derivative. Because remember, the derivative is the slope of the tangent line. If I draw in a tangent line, at a max, it is horizontal. At a min, it is horizontal. A horizontal line has a slope of 0, which is an x-intercept. So anywhere there's a max or a min on a function, there's an x-intercept there on the derivative. And finally, the degree goes down by 1 every time you take the derivative. So x to the fourth will be a cubic. A cubic will be a quadratic. A line, x to the first, will be a horizontal line, a constant. So we need to remember these relationships in order to do the first derivative and the second derivative test. All right, there we go. Okay, we're going back here. So the first derivative test, the first thing we have to do is we have to take the derivative. So we are going to take the derivative of this function, and that is power rule. So you got to get your power rule hat on for derivatives. So the derivative of x cubed is 3x squared. The derivative of negative 6x squared is negative 12x. The derivative of 9x is 9. And then the derivative of 3 is 0. So again, the degree goes down by 1. This is a cubic function. This is a quadratic function. All right, now we set the derivative equal to 0. So 0 is equal to 3x squared minus 12x plus 9. And of course, you want to work smarter, not harder. We are going to use the quadratic formula. And when we do that, we get nice whole numbers. This has an x value at 1, an x-intercept at 1 and 3. So if you remember, now we set up a number line, okay? And we put those x-intercepts on a number line. And then we use the derivative, label the bottom line as the derivative. We're going to use the derivative to tell us about the original function. So label your number lines. The bottom row will be the derivative. The top row will be the function. So this is the first derivative test. So in y equals, in your calculator, you want to be looking at the derivative. So put this into your calculator right now. All right, now you want to go into your table, and you want to start your table at 1, and you want to look to the left of 1 and to the right of 1. If you look to the left of 1, you see positive y values in the derivative. So we're going to put a positive here. That means the function is increasing there. Now when you look to the right of 1, you see negative y values there. And that means over that interval from 1 to 3, the original function is decreasing. Now we start our table at 3, and we look to the left and we check. Sure enough, to the left of 3, those y values in our derivative are still negative, so that's just double checking. But now to the right of 3, our derivative has positive y values. So that means to the right of 3, our function is increasing. Okay, so there is our number line. And again, our original function is a cubic. So there should be 3 turns, up, down, up. Now from this number line, we can find all this information. The increasing intervals is from negative infinity to 1 and from 3 to infinity. So this interval is increasing, this interval is increasing. So we just write those out with brackets. From negative infinity to 1 and from 3 to infinity. And then our decreasing interval is the one in the middle, from 1 to 3. So our first derivative test will tell us where our function is increasing and decreasing. Again, it is increasing and decreasing up here on the original function. The other thing that our derivative will tell us about is our max and minimums. Okay, so right here, when our function goes from increasing to decreasing, and I'm going to kind of put a dotted line there, from increasing to decreasing, that right there has to be our maximum. So our maximum is at 1. All right, we don't know the y value. And then vice versa, when our function up here goes from decreasing to increasing, there is our minimum right there. So our minimum x value, is 3. Now, to find these y values on our max and min, remember, it's increasing and decreasing up here on the original function. All right, so we plug these into the original function. So we need f of 1 for the y value for the maximum, and we need f of 3. So again, plug that original function into y equals up here, the original function, and find the y values. When I did that, I had a maximum at 1, 7, and I had a minimum at 3, 3. All right, so again, that is all the information that our first derivative will tell us about the original function. Now let's move on to the second derivative test. So the first thing we have to do is we have to take the second derivative. So we take the derivative of the derivative. So the derivative of 3x squared is going to be 6x. And then the derivative of negative 12x would be negative 12. And of course, the derivative of a constant, the derivative of 9 is 0. So our original function is x to the third, a cubic. Our first derivative is an x squared, a quadratic. And then as the derivative of the second derivative is a linear function. The degree goes down by 1 every time we take the derivative. So now the second derivative test, kind of the same thing. We set our second derivative equal to 0. So 6x minus 12 is equal to 0. And then we just solve for x. I can add 12 to both sides. So 6x is equal to 12, and then I can divide by 6. So our x-intercept on our second derivative is 2. All right, so now we set up a number line for the second derivative test. All right, so we put the second derivative on the bottom line, and we're going to use the second derivative to tell us about the original function. And of course, our x-intercept goes on the bottom. So again, we're using the second derivative to tell us about the original function. We are going to be looking at the second derivative in y is equal to. All right, so if we graph the second derivative, 6x minus 12, and we start our table at 2, to the left of 2, we have negative numbers on our second derivative. All right, and to the right of 2, we have positive y values on our second derivative. All right, now here's the thing. The second derivative tells us about concavity. All right, if our second derivative is negative, our original function is concave down. Concave down. And if our second derivative is positive over an interval, our original function is concave up. All right, now what is concave up and what is concave down? We're going to kind of go off to the side here. The easiest way I can tell you about concavity is what happens to the tangent lines as you go from left to right. Okay, let's look at this cubic curve. And I want you to, I kind of drew in some tangent lines for you. But as you move along this curve from left to right, the tangent lines get less steep. That means the slopes are decreasing. Whenever your slopes are decreasing, the tangent line slopes, that is what we call concave down. Our curve is concave down here. Now here, as we move from left to right, can you see the tangent lines get more steep? They get steeper, so our slopes are increasing. So if the tangent line slopes are increasing on a curve, that is called concave up. So again, concave down, the slopes are decreasing, getting less steep. Concave up, the slopes are increasing, getting more steep, the slopes of the tangent line. and the tangent lines themselves. Here, this is where it changes, and that's called a point of inflection, a change in concavity. So that's the easiest way that I can tell you how to think about concavity. Okay, so let's go back over here to our number line for our second derivative test. So, oh, good thing I can spell down here. Let's change that. Okay, all right. So our second derivative tells us about the concavity of the original function. All right, so here the concave up interval is right here. So we can list out that interval from 2 to infinity. Our original function is concave up. Our intervals of concave down is right here from negative infinity to 2. So we can list out that is at that interval, negative infinity to 2. And our point of inflection is right here. At 2, our function changes from concave down to concave up. So this right here is our point of inflection. All right, that is our POI. So the x value is 2. To find the y value, again, this changes concavity on the original function. So to find the y value here, we have to plug 2 into the original function. We need f of 2. You're plugging it into the original function. So we have to go way back up here to the original function and plug in 2. As always, use your calculator table. But when I plug 2 into the original function, I got a y value at 5. All right, so the second derivative test is right there. It tells you about the concavity of the original function. So that is a lot of information that we know about this function, and we never once looked at the graph. We know where it is increasing and decreasing. We know where max and mins are. We know where it's concave down and up, and we know where a point of inflection is. All right, let's do one more example together. Okay, example number 2, first derivative test. We take the first derivative. So the derivative of negative x cubed is negative 3x squared. The derivative of 4x squared is 8x. And then the derivative of 5x is 5. And the derivative of 20 is 0. So this is a cubic. When we take the derivative, the degree goes down by 1, so this is our quadratic. Now we set our derivative equal to 0. 0 is equal to negative 3x squared plus 8x plus 5. Now quad formula that. And we are not, unfortunately, we're not going to get nice, easy, even numbers. We have decimals. So I'm seeing negative 0.52. And I'm seeing 3.19. All right, so we have 2 x-intercepts, which makes sense for a quadratic. Now we're going to set up our number line. So again, on our number line, we put our x-intercepts on our derivative, negative 0.52 and 3.19. Our bottom row is the derivative, and we're using the derivative to tell us about the original function. Make sure your number lines are labeled. So these 2 x-intercepts split our graph into 3 intervals, from negative infinity to 0.52, from 0.52 to 3.19 is our middle interval, and then our interval over here is 3.19 to infinity. So again, this is the first derivative test. So we are graphing the first derivative. All right, that is what is in y is equal to. We graph our derivative right here. And we start our table at negative 0.52. When I graph my derivative and look into my table at negative 0.52, to the left of it, I see negative y values. And to the right of it, I see positive y values. Okay, so that means here, if our derivative is negative, our function is decreasing there. And here, if our derivative is positive, our function f of x is increasing there. All right, now I'm going to start my table at 3.19. Again, I'm still looking at the derivative. At 3.19, I check. To the left, do I still have positive y values in my derivative? I do, so that's just checking this middle interval. To the right of 3.19, I see negative y values in my derivative. Yes, negative. So now it looks like my function there will be decreasing again. All right, so since this is a cubic, my original function up here is a cubic, I should have 3 turns. Down, up, down. It looks like right here, because we're going from decreasing to increasing, this is my minimum. And since we're going increasing to decreasing and it changes right here, this is my maximum. All right, so now I just fill out my information. I have only one increasing interval. It is the middle interval, negative 0.52 to 3.19. It is increasing. My original function is increasing right in here. I have two decreasing intervals. My left interval is from negative infinity to negative 0.52. It is decreasing up here, and then my interval over here, it is also decreasing. So I have two decreasing intervals, 3.19 to infinity. All right, for my max and mins, my maximum is at 3.19, and my minimum is at negative 0.52. Remember, you plug into the original function. Plug into f of x, the original. Those max and mins happen up here on the original function. So when I graph the original function, my y value for my maximum, again, they're not very nice numbers, is 44.19. It's way up there. And then my y value at the minimum, I'm seeing 18.62. All right, so just by looking at the first derivative, we found all that information. Now let's do the second derivative test. Okay, for the second derivative, I take the derivative of the derivative. So the derivative of negative 3x squared is 6x, and the derivative of 8x is 8. All right, so let's get our second derivative down. Negative 6x plus 8, and it should be linear. Now we set it equal to 0. 0 is equal to negative 6x plus 8, and we solve for x. I'm going to subtract 8 from both sides. So negative 8 is equal to negative 6x. Good old algebra. I divide by negative 6. So these are going to cancel. My x is equal to positive 8/6, or 4/3, or, if you like the decimal, 1.33. Either of those is acceptable. Okay, now we set up the number line. Again, you put your critical point, your x-intercept there. This is the second derivative test. So we are looking at the second derivative, and it's going to tell us about the original function. Make sure your number line is labeled. All right, so the second derivative is in y equals. We start our table at 1.33, and we look to the left, and we look to the right, and look at what kind of y values our second derivative has. I'm seeing positive y values here and negative y values here. So positive to the left, negative y values to the right. So that means that up here, our original function is concave up, CU. You can abbreviate concave up. And then over here, because our second derivative has negative y values, our function, our original function, will be concave down. Or you can use abbreviations, whatever you like, concave down. All right, it changes concavity right here, so this is our point of inflection, POI. All right, so there's our second derivative number line. Now we just put all our information down. Our concave down interval is right over here. It's the interval on the right, so this is concave down. So 1.33 to infinity. Our concave up interval is our interval on the left. So we label that as negative infinity out to 1.33. Right here, negative infinity to our critical point 1.33. And our point of inflection, our x value is 1.33. And we use parentheses because this is a coordinate point. Now remember, this changes concavity up on the original function. So here, to find this y value, you plug into original function. Plug into original. All right, our original function. All right, so it's f of 1.33. All right, so our point is 1.33. When I plug that into my original function, remember the original function is way up here, our original cubic function. When I plug 1.33 into this, I'm looking at my calculator right now, I see a value of, 31.37. So there is our point of inflection. All right, so there is the first derivative test and the second derivative test. Miss you, calculus. You should probably come see me on Google Meet this week. All right, later. Take care. Toodaloo.